Alrighty, so in this lesson, we're going to be talking about searching. So that's going to be one half of our section, searching as opposed to sorting. Oh, I got to click that. Alrighty, so our lesson objectives. We're going to learn the standard algorithms for searching, and we're then going to apply linear search to search for information in an array and an array list. And we're going to do the same with binary search. So what are searching algorithms? Searching algorithms allow the compiler to find a desired value by finding its appropriate position by comparing two values, right? So that one value is going to be your target value. That's the value that you're trying to find. And then the other value is the value that you're comparing it to. So if it's the same value, then it's going to return true. You found the value. If it's not the same value, it's going to keep on looking, right? And if it's unsuccessful in that case, then it's not going to return any value simply because it couldn't find a value. And two examples of these searching algorithms are linear search and binary search. So linear, otherwise known as sequential search, is basically your most basic type of search algorithm. How it works is the algorithm is going to check the first element it sees, and if it's equal to the value that we want, then it returns true, or the location at where it's at, depending on what you want, right? And if it doesn't go, or if it doesn't find the element, then it just moves on to the next one, right? So you're like, alrighty, let's look at this one. Alrighty, it's not that element. Let's move on to the next one, the next one, the next one, the next one. It's like reading a dictionary, but instead of, searching for the word by going to the word section or the letter section, let's say if the word I want is whack, right? I'm not going to the W section directly. I'm going from A, B, C, and all those sections until I see whack. And then that algorithm continues until it finds the value or reaches the final element. So let me give you a demonstration of linear or sequential search. We have 6, 9, 4, 5, and 0, and we're trying to find 5 through linear or sequential search. Now, I know this might be easy for you, but let's see what a computer would do if we designed the algorithm to find it through linear or sequential search. So it's like, alrighty, 6. Is 6 equal to 5? And I have the double equal sign because in computer terms, that is it comparing 6 to 5. Is that a true statement? Is 6 equal to 5? No, 6 is not the number 5. So it's false. Alrighty, that's not too bad. Let's go on to the next one. Is 9 equal to 5? Yes, it is. Oh, sorry, no, it is not. Right, I was looking at never mind. But 9 is not equal to 5, so it's false. Alrighty, let's move on to number 4. Is 4 equal to 5? Nope, that is false. And is 5 equal to 5? Yes, that is a true statement. So it ignores 0, right? Unless you design the algorithm to find the last occurrence of 5 or to make sure that it sees every single value. But in this case, right, it's going to stop when we find the number 5 and it's going to return true. Hey, we found the number 5. So what is the best case and worst case scenario for linear search, right? Because when you're thinking about algorithms, you want to make sure that you have the most efficient algorithm. So the best case of this scenario would be if the element is found on if the element is the first element. So if you have a element, let's say if we were looking for 5 in the previous example, right? The best case scenario of this linear sequential search if it would be if 5 was over here, if it was the first element. And there are two worst case scenarios. One is if it's not on the list. And if it's not on the list, that means it had to go through every single element one by one, all in that order in order to find that element, in order to find an element. So if it doesn't find it, then it went through every element and it found that it wasn't there. Or if it's the last element on the list because it went through every other element prior to that, and that was the last one. And with that being the last one, then it found it. Alrighty, binary search is a little bit more different, right? And it's a lot more efficient, which shows the beauty of computer science. So this requires a sorted list, meaning that everything has to be, if it's a numerical list, right, then it should be listed in 1, 3, 5, 7, 9, in that type of order, 1, 2, 3, 4, 5, numerical order. It has to be a sorted list, as opposed to sequential search, which didn't really require a sorted list simply because it would just go one by one by one by one. This requires a sorted list simply because that's how what the algorithm is developed upon. So the binary search will find the position of the first and last value, and then using that, it calculates or finds the position of the middle value. Then it does three comparisons depending on which one of them is true and which one of them is false, right? It might do one comparison, might do all three, right? And it's going to see already, is the middle the exact value, right? So if we're trying to find a value, is the middle the value that we have? If it is, then it's going to return that position, right? Because we found the value on the first attempt, right? But if it's not the value, what it's going to do is going to do two types of comparisons. One comparison is going to see if the target value is greater than the midpoint, because if it is, then we can move our left endpoint to that position. So we've already eliminated half of our workbook, right? We've already eliminated half of our array or half of our data set simply because we know that the target value, the value that we want, is greater than the midpoint, because this is a sorted list, right? So if it's greater than the midpoint, that means it cannot be any value before the midpoint. Same thing, well, same concept rather, is if the midpoint is greater than the target value. If the midpoint is greater than the target value, if the midpoint is greater than the target value, then we know that it can't be anything greater than the midpoint, right? Anything past the midpoint, we already know, or the computer already knows that it won't work simply because we already know that the midpoint is greater. So anything past the midpoint would also be greater. So it already eliminates, just like in the previous comparison, half of our data set, half of our numbers. And it continues doing that until it fails if it can't find a value, or if it does find the value. And this is generally faster than sequential search, right? So the average runtime will be faster than the sequential search, because sequential search, it goes through every single element one by one by one. But that doesn't require a sorted list. Binary search, on the other hand, requires a sorted list, but it's much more efficient if you do use binary search. So let's do an example. Let's find number 422 with binary search. Okay, so we find the first position, and the first position is 0, alrighty, because in arrays or array lists, right, because that's what we're going to be mainly using for now, right? Maybe if you go on to advanced classes, you're going to be using much more efficient and more advanced data structures, but for now, we're going to use arrays and array lists. So the first position is going to be 0. Then we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so we have 9 here. Okay, let me move me a little bit up there. Alrighty, so we have 9 over there. So what is 0, which is our low point or left point, and add that to 9, which is our right point, our high point. And we're going to try to find the midpoint through that. So 0 plus 9 is equal to 9, and 9 divided by 2 is 4.5. Now, because we're dealing with integers, right, we're going to round that down to 4, right? Because if you know, if you remember from our divisions early in the chapter, early in the class, right, when you're dividing integers together, usually it will just cut off the decimal. It'll cut off the decimal because it returns an integer answer. So 9 divided by 2 is going to be 4.5, but then it cuts off the 0.5 and it's going to be 4. And that is position 4. So now it does a comparison. I just voice cracked a little bit there. Alrighty, is 402 422? No, it's not. So is 422 less than 402? No, it's not. And 422 greater than 402? Yes, it is. So what it does is it eliminates all of these values, right? It eliminates all of those values simply because we already know that 422 is greater than 402. So it can't be any of these values before the midpoint. So it can't be 68, can't be 124, can't be 205 or 354. But remember, that's just our conscious. We can do that very fast, or rather we can do that We could do that just by simply looking at it all together. But what a computer is going to do, if it does it through sequential search, it's going to go, yeah, no, 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 no. And that takes a while, right? Especially with very, very large data sets. We don't want to use sequential search on such very, very large data sets. But just to show you this example of how efficient it is, we've already eliminated half of our sorted data set simply because we know that 422 is greater than the value at our midpoint. Alrighty, so now we're left with these values. We're left with this new low value, which we're going to set as 0. So that's going to be our new 0 or a new low point. Alrighty, so that's going to be our new low point. And our new high point is going to be 1, 2, 3, 4. And that's going to be our new value, 739. Well, we're not going to look at 739, but we're going to look at position 4. Position 4 is going to be our high point because it is the biggest value on our sorted array or array list. And then if you look here, that is going to be our low value because that is the first it's the value at the first position. So to calculate the midpoint, we need to add these two values together and then divide by 2. So 0 plus 4 is equal to 4. And then we divide that by 2. So now our value, our midpoint, is going to be 2. Is 690 greater than, oh, sorry, is 690 equal to 422? So it looks, already, is 422 equal to 690? No, it's not. Alrighty, so we know that the midpoint is not the value. But what can we eliminate now, right? Because let's make it more efficient and eliminate another half of our data set. So is 422 less than 690? Yes, it is. So we can eliminate 690 because that's not the value, right? And then anything greater than 690, right? Because we know that 420 is less than 690. So it can't be any value greater than 690. Again, it's a sorted array list, right? I have to keep coming back to that because the binary search requires a sorted list, a sorted array or a sorted array list. Alrighty. So we're left with 2 values. And we're like, alrighty, we have our low point, which is going to be 0, and we have our end point, which is going to be 1. So 0 plus 1 is going to be 1. Divide that by 2. And to find the midpoint in this case would be 0. So that is also going to be our midpoint. And we compare that to 422. Is 422 equal to 422? Yes, it is. So that is going to be our value, or that is going to be our target, right? So we did find, it's going to return true in this case. We did find 422 through binary search. Now, you're probably wondering, this took such a long time. Why are we doing this? Well, understand this, right? It might have taken a long time, but we've basically done, if you look in, actually, let me avoid that slide because then I'm going to have to go through it again. But if we did this through sequential search, right, we would have had to do 1, 2, 3, 4, 5, 6 comparisons, right? We would have been doing 6 comparisons, right? And it would have checked it every single time until it found that value, right? But say if 420 was the biggest value, then it would have done it all the way to, it would have done it every single value, every single time. So what happens is in this case, in this scenario, we've really have only done 3 comparisons as opposed to 1, 2, 3, 4, 5, 6, right? We've done 1 comparison, right? So we found out that, it's 400, well, rather 2 comparisons, but in this case, we did it in much faster time than we would have with sequential search. So basically we have 3 levels to this, whereas we would have had 6 levels if we went through the sequential search area. So the best case and worst case scenario for binary search, the best case, just like sequential search, is if the number is found on the first try, but unlike sequential search, it's not going to be like the first value in the data set, right? It generally looks at that last or one of the last few items. So if the number is right in the center, then that is the best case scenario, if it's exactly the midpoint. And the worst case scenario, just like sequential search, is if it's not even on the list or if it's the first or last element of the list. We could also do the worst case scenario calculation, and generally this requires learning up to the the 2 to the power of what. So we first have to know how many elements we have on a list, right? Um, well, let me tell you actually how to calculate it. We have to round the number of elements to the nearest power of 2, then find the exponent. The number of the exponent is the number of comparisons, basically. So that's going to be our worst case scenario calculation. So let's say if we have a, number of elements, a 12 number of elements. So that's going to be our array size minus one, or yeah, array size, or yeah, that's going to be our array size or array length. And basically we try to find the nearest power 2 to the power of what equals or is close to 12. So we round to the nearest power of 12. So we bump it up to 16 because 16 is a multiple, not a multiple, but like it's 2 to the power of something. And what is 2 to the power of something equal to 16? Well, 2 to the power of 4 is equal to 16. So 4 is the number of comparisons, right? So we bump up the number to 12, from 12 to 16, and then we write 16 in terms of 2 to what number. Alrighty. So we try to find the closest 2 to the power of what number, 2 to the power of what exponent, and the exponent of 2 to what value. That value becomes the number of comparisons for the worst case scenario. So let's move on to the compiler and actually code both of these algorithms together, right? So generally speaking, you're going to be provided this type of algorithm on the AP exam, but I feel like to actually understand what's going on with this calculation or with the searching algorithms, you kind of need to get your hands messy with the code. So what I'm going to do is I'm going to switch over to the compiler. Hopefully I'm on the right screen. I'm using a different screen sharing software. So let's see. Okay, so we're good. We're good. Alrighty, so let's first do linear search. And again, linear search, what it does is that it goes through every single value and then returns true if it finds the value, and if it returns false if it can't find the value. So there's only really one comparison, and that one comparison is, well, if it equals. If it doesn't equal, then it just moves on to the next one. So what I'm going to do is I'm going to create a helper method, a public helper method, public static void, and I'm going to call this linear search. And it's going to take an array argument, and I'm going to call it my array. Now, what type of an array would we want? Well, let's do an integer array. Right? I don't want to mess with 2D arrays because that's going to get a little bit messy, but we can work with what we've got, and we're going to work with an integer array. Alrighty, cool. So now we have an integer array. And what it's going to do is it's going to traverse through a array, and it's going to return true if it can find the value. So what we're going to need to do, right, if you know from our method declaration, we need to change our return type from void to Boolean. Void implies that we are returning nothing, so we're not going to have a return statement in a void method in a method that has a void method declaration, but we're returning true or false. So we need a public static Boolean. We need a Boolean return type in our method declaration so that we can return a whether or not if the linear search algorithm finds the value. Alrighty. So what it needs to do is it needs to traverse through let me actually, to prevent any errors from happening, I'm going to return null for now, and then I'm going to show you how we do the search algorithm. So return null is just so that it doesn't have any compilers errors right now, or the compiler's like, yo, you're not working right now, stuff like that, right? So we need a return statement in that case. But what I'm going to do is I'm going to do for, we could do integer I, or you can use a for each loop. There's no problem with that, but I'm going to use a integer I loop. And then we're going to be like integer I is equal to 0, because remember our array list our array. I keep getting them confused. Our array is going to start at position 0, and it's going to go up to whatever the value of length is minus 1, because length tells you the number of elements, and you got to subtract that by 1. So it's going to be like my array. So this is going to be our Boolean expression. So if this Boolean expression becomes false, then it's gone through the entire array. My array, oh, sorry, not my array. It's going to be I is less than my array dot length. And we're going to increment the value of I after each loop has been executed. Wrong brackets. Alrighty. So we have a for loop declared, and what the for loop is going to do is it's going to traverse through our my array, right? So how do we traverse through an array? So when we traverse through an array, the way that we get the value is we first say the value of the array. So what is the identifier of the array? And then we're like, alrighty, how do we access an element of the array? And the way that we access the element of an array is by having these opening brackets and then inserting a number here. In this case, it's going to be I, integer I, because it's going to start at 0 and it's going to keep on going. It's going to test it's going to find every single value, until it finds the value of the array. So that's how you get a value in the array. So let's name this integer current number is equal to my array. Okay. So now we're getting the first position. So with every iteration, it's going to check what value. So it's going to start at 0. It's going to first access the first element of the array, and then it's going to, for every iteration of the for loop, it's going to be a new number. Alrighty, and what is our target? So in that case, we also have to add a target into our linear argument, into our linear search algorithm. And this target is going to be the value that we're going to be trying to find. So we've already declared it in our method declaration. And when someone sends that value, we've already declared it. Integer target is going to be equal to, let's say, just like in the previous example that I showed on the slides, 5. It's going to declare it there. So there's no need to declare it here or here. I mean, you wouldn't declare it here because it would go out of scope anyway. So now we got to find out whether or not target equals this value, right? Current number, the number that we're looking at right now. We have to find out if that's the value that we want. So what better way to do that than using an if statement? So we're like, all right, if current number is equal, remember the double equal sign, is equal to target, what we're going to do is we're going to return true. Alrighty? Oh, and forget the semicolon. Alrighty. So it's going to go through every single element until it finds if the current number, or the number that we're looking at the array, is equal to the value that we want to find, equal to the target. And if it goes through that entire for loop and it never invokes this if statement, right? I mean, it's going to check, it's going to do this comparison with every single value, but we want to reach here, right? And if it never reaches here in this entire for loop, then we know it's going to be false. Oh, there you go. And we know it's going to be false because after looking at every single element, the fact that this never returned true means that it couldn't find the element within our array. So it returns false if this for loop gets done. Because if this is ever invoked, right? If this ever if this if statement is ever true, then it would return true and it wouldn't even look at the other elements, right? Because as you know, with return statements, it just stops the method. It stops whatever it's doing, even if there's other lines, such as in this case, there's a return false statement. It won't even think about executing return false because it returns true, right? It stops right there. The method's like, alrighty, we're done. We're returning true. So let's test out our search algorithm. So let's do integer. Let's do a number array. And unlike binary search, which we'll get to later, we need to, unlike binary search, we don't need a sorted array because it's going to go through it one by one. So let's do it through this. 5, 6, 10, 3, 9, 567, 98, and 69. So we got some nice numbers here. Up, and let's put a semicolon. Alrighty, so we have a array, we have a list of values, right? And now what we're going to do is we're going to do a binary search on it. Linear search. So let's send this array into our linear search method. So we have two arguments. We have our my array. So this is the array that we're going to be doing our linear search on. And then we have to find the whatever value that we input. So let's first insert number array. And then let's see if it finds 567. And with that semicolon. So what this print statement is going to do is it's going to print true if it finds 567, and it's going to return false if it doesn't find 567. It should return true. Why? Because 567 is in our array list, is in our array. So let's run it. Actually, let me first save it. Now we run it. And it returns true because it finds the value 567. But let's put a number that's not on there. Right? So we have an integer like this. Alrighty, and let's run it. And it returns false because what it does, it's like, alrighty, let's send this array into our linear search and let's send this value as our target. Alrighty, so we're doing our experimentation with this array and we're doing our target. Well, with this, we're trying to find what the value, if any value in our array is equal to target. So is 5 equal to whatever this number is? No, it's not. Is 6 equal to whatever this number is? No, it's not. Is 10 equal to this, whatever this is? No, it's not. It's going to keep on doing that. And it's going to be like, alrighty, is 69 equal to this? No, it's not. So now the for loop has gone through everything. It's gone through every single element within our array, right? And it has never returned true. It has never returned true, right? Because if it returned true, it would have found an element. So once our for loop is done, our computer knows, or rather the algorithm that we developed knows, there is no number like this. Yeah, there is no 2,345,678 within our array, so it returns false. Alrighty, so we've pretty much done with linear search, right? Linear search wasn't half bad. Binary search is a tad bit difficult. And with binary search, there's actually two main ways rather of doing it. One is the iterative way that we're going to do today, right? We're going to use a while loop and it's going to keep on updating the value of midpoint, low, high, whatever value that we have. And what it's going to do is it's going to keep on doing that until it finds the value. And if it doesn't find the value, then, we can't find the value. So let's do it. Now, unlike this array, right? Unlike linear search, it does require a sorted array, because if it's not a sorted array, then it's just going to screw up the values. So we don't want that to happen. So public static, and I'm going to copy Boolean here simply because we're going to do the exact same thing. We're going to return true if it finds the value, and it's going to return false if it can't find the value. Let's do binary search, and it's going to do integer my array, and we're also going to have integer target. So just like our linear search, we're going to have integer my array, but as a precondition, however, hope I spelled that correctly, my array argument should be a sorted array. Integer array. Again, have those curly brackets so that we don't get any problems. Alrighty, so what it's going to do is it's going to first, what we want to do is we're going to first have to find the value of integer low. So integer low is going to start off at 0, right? So that's going to be the first value of our array. What position is the first value of our array? And then we're going to have an integer high. An integer high is going to be equal to the array length minus 1. And the reason why we put minus 1 is because, remember, we start off at 1, right? Remember, we start off with 0. We don't start off with 1. So everything gets subtracted, and length returns the number of elements, so we don't want to make that mistake. Alrighty, so that's going to be our value. Alrighty, so now what we're going to do is we're going to create a while loop. So in our while loop, what should we put as our Boolean expression? Well, the Boolean expression, or a Boolean expression to actually execute it. The one that I'm going to use is if low becomes great, if less than or equal to high. And the reason why I want this to keep on executing like this, if the while loop will only execute if low is less than or equal to high. And the reason why I want to do that is because once low is greater than high, then we haven't really found the value after doing binary search. After our binary search algorithm starts making values that makes low the greater value than high, then we haven't found the value, and we need the while loop to stop at one point. And that one point it will be when it realizes that we haven't found the value. We keep cutting it, and now we're mixing and maxing all together. So we want to avoid that situation, and we're like, alrighty, if while low is less than or equal to high, then keep on executing the while loop, or rather until it finds the value when it returns true. But we'll account for that with our if statement. Alrighty, so now it needs to calculate the value of integer mid, right? And just like I told you in the example in the PowerPoint, integer mid, right, or the midpoint, is going to be the value of low plus the value of high, and we simply divide that by 2. Alrighty. Calculate mid. So midpoint is going to be the value that it's the position that we're trying to find. So it's going to be like, alrighty, not for, we're going to have an if statement, and what it's going to do is it's going to see if the midpoint is the target value. And how do we do that? We use an if statement. So we access the element of our array through the midpoint position. So remember, the midpoint isn't actually the number that it's not the number that's in the array. It's not an element. I mean, it could be, but what I'm trying to say is mid doesn't represent a value. It represents a position. So we're going to use that position to access a value in my array. So my array, and we do all these open brackets, and now we're accessing the midpoint value, right? This is the midpoint position. This is the midpoint value, right? And this is an integer. This is also an integer, but this is an integer representing the position. This is an integer representing the value at the midpoint. And now we're going to see whether or not if that equals to the target value. Now, if this equals the target value, then I want to return true. Alrighty. So if this is the value, if we find out that the midpoint is the target value, then it's going to return true. Otherwise, right? And in this case, we're going to do an else if statement. Else if. Now we got to do 2 more comparisons, right? Now we could do technically 1 comparison and have an else statement, but I want to make sure that you get the concept down, because you can do this many other ways. So let's do the exact same thing, except change the logical operator that's in there, or the Boolean value, okay? And we're going to have target. So now we're like, alrighty, my array, what if the value of target was actually greater than the my array mid? Make sure that I have that good so it doesn't give me an error. Alrighty, what if the value of the target, so the value that we're trying to find, is actually greater than the value at the midpoint? Well, that eliminates pretty much like, anything that's below or behind the midpoint, right? So anything that's before the midpoint, we don't really need anymore, right? We don't need it, right? Because we've already know. I mean, again, this with the precondition that it has to be a sorted integer array. I'm going to keep coming back to that. It should be a sorted integer array, or rather, a sorted array, right? Because you might be doing doubles and stuff like that. But in this case, right, it's an integer. In this case, it's an integer. But we already know that if the target or the value that we're trying to find is greater than the midpoint, the value at the midpoint, then anything that's less than the midpoint that is in our data set can be pretty much eliminated, because all those values are also less than the target, and they're probably not going to be the target value in a sorted list. So what we could do is we can actually set a new value for low, right? So now low will no longer be 0. Low will be mid plus 1, right? Because now we could have set this as the value of mid, but we already know from this Boolean expression that it's not the value of mid, right? The value mid can be eliminated. So we set it as a value that's greater than mid. Now, we could put this as an else statement. Again, I'm not going to do that simply because I want to make sure that you guys get the concept down. Alrighty. And just like that, I'm going to put the target there too. Now, what happens when the value at the midpoint is actually greater than the target value? Right? What does that mean? That means that the target value is less than the midpoint. Well, then we know that anything that's greater than the midpoint, well, if the midpoint is greater than the target, then literally any value that comes after the midpoint is not going to be the value of target, because all those values are also greater than the target. So what we can do is that we can actually shrink down our high, right? Our high can now be mid minus 1. And again, just like our previous example, right? Just like with low, right? Because we know that the value is not mid because we've already tested mid, right? And again, with the while, I'll explain why mid keeps changing. But in this case, the value of high is no longer going to be the array dot length size. It's going to be mid minus 1, because we know that it's not going to be mid, right? And it's not going to be anything after mid. So we can't do mid plus 1. So we have to do what's underneath mid. So the new high is going to be mid minus 1. Alrighty. So that's going to be our while loop, right? So it's going to keep on taking values. So the original array list is going to first get tested, right? Or the original array. I keep making that mistake. That isn't really the point. But the initial low and high is going to be 0, and my array dot length minus 1, because that is the first position and the last position. And then the midpoint is dividing that by 2, right? And then it's going to be like, alrighty, if we find the mid, then we're going to return true because we found the mid, right? Also, if it doesn't find the mid, right? If the target is actually greater than the midpoint, so if the value is a little bit after the midpoint, then we can just increase or eliminate half the competition, right? Half the competition meaning any value up to the midpoint, including the midpoint. So we got to increase the value of low to mid plus 1. Otherwise, if the target is in fact less than the value at the midpoint, meaning that any value after the midpoint, including the midpoint, is greater than target, then we can eliminate any value past midpoint or including midpoint, right? And what it's going to do is it's going to go back all the way to the top, check if this comparison is true, right? Which will most likely will be if it has to do multiple comparisons. And then it's going to rerun the midpoint calculation with the new low that we calculated or the new high that we calculated. And it's going to keep on doing that until it returns true. But what if this returns false? Well, if this returns false, that means that we haven't found the value, right? We haven't found the value. So in that case, right, we have to return false. And that's only if the while loop gets entirely executed right, to the point where this fails. And once this fails, we know that the binary search algorithm hasn't found the value. That's a little bit there. Hasn't found the value or the target value within my array. And it returns false in that case. But if the value is in that sorted array, then we have found the value in our array and we return true. So if the value is in that sorted array, then it will return true. But if this while loop algorithm eventually goes up to the point of failure, right, then it can't, the binary search algorithm hasn't found the value and it returns false. And it will only return false if it reaches this statement over here, right? Otherwise, it would have just stopped the algorithm altogether if it returned true in this statement. And that statement, it can only be executed if it finds the value and returns compares it with target and returns true. So let's test it out. So unlike our linear sequential search, we have to have a sorted array. So let's do 1, 5, 9. I'm just guessing numbers right now. So let me do 12, 36, 45, 57, 89, and 100. Okay. And 89. Okay, good. 1, 5, 9, 12, 36, 45, 57, 89, and 100. So those are all values these are all values in a sorted array, right? So this is already sorted. I sorted it myself. Again, we're going to make a sorting algorithm that will sort them all together in another video. But just for the sake of this video, we're going to test it out. So let's see if our sorting algorithm can find the number 36. Actually, let me make sure. 1, 2, 3, 4, 5, 6, 7, 8, 9. Alrighty, 9. Alrighty, 36. And let's change this from linear search to binary search. Alrighty, so we have our array argument and we have the integer argument that will be our target value. So we're trying to find 36 and it should return true. Because 36 is in fact within our number array. Save and run, and it returns true because it finds the value of 36 within our array. But let's see, let's try it with 37 actually. And 37 doesn't work because 37 isn't out within our array. It goes from the midpoint, it eliminates, let's say with 36, it would have gotten it right over here. But with 37, what would have done, it would have been like, alrighty, 0, 1, 2, 3, 4, 5, 6, 7, 8. What is 0 plus 8? 0 plus 8 is 8. Divide that by 4. And the midpoint would be 0, 5, 9, 12, 36. It would have been 36. So that 36 is our midpoint. Is 37 greater than or is less than or greater than 36? 37 is, well, 37 is not 30. 36 is not 37. But after that, it would have been like, alrighty, 37 is greater than 36. So we've already eliminated half of the competition there, right? So now we have 45, 57, 89, 100. So it's like already 0, 1, 2, 3, 3 plus 0, right? 3 plus 0. I mean, we have different values. It's actually using the same values that we have with our integer, but just for the sake of, simplicity for us, it's like, all right, we've already eliminated half of that competition anyway. It's like, alrighty, our new midpoint is going to be 57. Alrighty, 57, is that greater than or less than 37? Well, that is 37 is less than 57. So it's going to be like, all right, let's eliminate this competition. We've only have one value left, so it's going to just compare it against itself. Is 45 equal to 37? No, it's not. Well, then this entire while loop then fails because our low high and high low are now not being well with each other, right? So this Boolean expression ends up failing and it returns false. So that is why we have our algorithm. That's how basic our algorithm works, but it does so in a minimum amount of comparisons, right? So it basically did that after three comparisons, or rather three runs of the program, three iterations of the while loop. Whereas what the sequential search would have done, it would have gone 1, 5, 9, 12, 36, 45, 57, 89, 100. And it would have returned the same answer. Actually, we could test that out right now. So linear search wrong. We can test that out and it will return the same value. It's going to return false, but it did so after, going through every single element. It has a very high worst case scenario in that regard. And that is a basic introduction to searching algorithms. We covered both linear, the easy one, binary search, which is a little bit difficult to understand. But once you look at every single value and how it works, you find how it shows the beauty of computer science by basically cutting in half or rather making it a much more efficient algorithms. And that is what computer science is about: efficiency with our data sets.